The next presentation is by Jennifer Donahue. She digged into the simulation the data to come up with the new hanging wall model. Empirically, we don't have so many recorded motion at hanging wall versus footwall, different angles and different magnitude and so on. Jennifer digged into the simulation and she's going to present the result. Thank you very much.
Thank you, Yusuf. For those that know me and have been going through the NGA meetings, I've cut my normal slides down from the normal 250 to about 12, so you should be pretty happy. Also, I'm just in the middle of getting over my cold, so I'm a little bit more baritone than normal. I'm Jennifer Donahue. I work for Syntech. I want to say a special thank you to Norm Abramson. He helped me develop this model. So when we started looking at, as Yusuf said, how are we going to develop the hanging wall model that we're going to bolt on to the GMPEs for the developers, we first looked at the empirical data. We limited it to both the footwall and the hanging wall and the stations that had a source-to-site angle of plus or minus 90 degrees. And what I mean by that is that if you take a look at where the stations are, there we go. So this is a station map. Let's say that this is the surface trace of the fault. This is the fault is it because it's a reverse fault. This is at depth. We're looking at if it's minus 90 degrees, it's in this direction. If it's plus, it's in this direction. So we're really looking for what stations do we have that are in the plus and minus 90 degree area. And there weren't that many to begin with. So we have Northridge, Chi-Chi, Nagata, Wenchon, Iwate, Loma Prieta, and Locula. So there really wasn't a lot that we could try to constrain the hanging wall model with. So with that, we turned to hanging wall simulations. Graves in 2011 and 2012 developed a velocity model. It's currently on the broadband platform. And there were several models that were run by Albert and also by Ronnie and for Katie. So there was 34 reverse cases that were looked at. For surface faulting, there was 5 different magnitudes ranging from 6 to 7.8. There was 5 different dips, so from 20 to 70 degrees. There was also some buried ruptures that were looked at, and these had a top of rupture of about 5 kilometers. But there was only 2 magnitudes that were looked at, and so that was a 6 and a 6.5, and the dips only went from 20 to 60 degrees. The lengths and the widths, the faults were only varied for the magnitude 7 and 7.5. And what I mean by that is for magnitude 6 and 6.5, it was the same length and width for each one of the cases. So it was always a 10 by 10, 10 kilometers length, 10 kilometers width. That was basically rotated down for the magnitude 6. Also, all of these simulations had a VS30 of 865 meters per second. So this is your eye chart for today. Hopefully those in the back can read it. This is all available in a currently unpublished peer report. So where's the mouse? These are basically all the simulations that were run. And as I was saying, for the 7 and the 7.5, the widths and the lengths were varied for the different scenarios. And so using this information, we regressed on the footwall. So we took a look at the area through just in the minus 90 just to begin with, just so that we can start to build our model. And we did a regression on this, and we used Rx to begin with. So going back to the information that we had on the flat file and the different characteristics that we have for Rx, Ry, Tu, some of these other terms that we used, just as a reminder, when we're going in this direction is Rx minus, and if we're going in this direction is Rx plus. So we used Rx for the R term, so this is the functional form. And then there's a couple of terms that go with that as well. So these are the different regressions. These B terms, I've made those available to the developers, and again, they'll be in the peer report. So we used that, and then we applied that same equation onto the hanging wall side. So we took the footwall, which you see here, we applied it over here onto the hanging wall. And because we're using RUP now, because Rx in the minus direction is the same thing as RUP, we're using it now on the hanging wall side. You can see that it's a little bit different. It's not a mirror image of each other because RUP is different as you go in different Rx as you go away from the fault. So we developed this based on our footwall. Then we found the median from the simulations. So there was 30 realizations for each one of the simulations. And so, for instance, if we look out here at minus 35, each one of the dots that you see here was a different realization of that event. So we took the medians, and then based on that, we did a non-parametric model for the hanging wall. And that's what you see here as the blue line. So this is the hanging wall function. So it looks kind of big. It's actually really easy to implement. We have, Yusuf was coming up, but I thought I was already out of time. Okay. Okay, so here's our functional form. Again, each one of the developers is going to have their own functional form. So they're going to have that. They're also going to have their own dip term, and they're probably going to have their own buried rupture term. That's in their base models. So the hanging wall term is the bolt-on term that they're able to use for their models in addition to that. So there's different tapers. The first one is an A1 term. So this is what the modelers can use to scale the hanging wall model up and down according to how they develop their functional form. We have our second taper, which is a function of dip. We have a taper for magnitude. This is our distance taper. This is our depth taper, and this is coming off the sides as we go along, in source to side angles of greater than 90. So I'll step through each one of those. So for our T1 term, which is our dip term, what we tried to do is center it on 45 degrees. So it's pretty easy. We know what our dip is. And basically, this is the dip taper. Again, it's an amplitude of 1 at 45 degrees. Moving on to the magnitude taper, which is T2. Again, very easy to implement. 1 plus A2 times M, and centering it again on 6.5. Just want to point out that the simulations only went down to a magnitude of 6 and only went as high as a magnitude of 7.8. So it's hard to extrapolate between the two. So here's just the magnitude taper. Very easy to implement. 6.5 is right here, so you have an amplitude of 1. Moving on to the distance taper. So this one's a little bit more complicated, and I'll step through this. Excuse me. If your Rx is less than 0, so as I said before, this is on the footwall side, so you have a minus Rx, there's no hanging wall term, so the whole term zeroes out. Okay, if your Rx is less than R1, and so I defined R1 here as the width times the cosine of the dip. So really, if you look at it, if anybody knows the joiner bore distance, it's basically if you're right on top of the fault plane, that's R1. So if you're within the R1 distance, you use this F1 term, which is here. If you're outside of that joiner bore distance of 0, if you keep going out to a distance of R2, which is defined here by this term here, it's a function of magnitude. If you're outside of that, you're going to use the F2 term, which is here. And then if you're outside of that, then you're going to use the F3 term. Okay, and so what that looks like is this is basically all that it is. So if you're at an Rx of 0, you're coming up until you get to an Rx of 1. So you're increasing the amplitude as you're going out over the hanging wall until you get to the very edge of the hanging wall, which is here. So this is the edge of the hanging wall. Then as you're coming off the hanging wall, then you're going to start decreasing. And what we found at a certain distance, it really fell off to nothing. And so at that point, you're basically right back on the footwall model that's now on the hanging wall. So we took an exponential term, this F3, and so as you can see here, it dies down to 0 very, very rapidly. Okay, so that's the taper. If you want to look at that, how that looks over different magnitudes, so these are all magnitude 6, 6.5, 7, 7.5 at 30 degrees. You can see how the taper develops as you're kind of going out away as you get larger and larger magnitudes. The next term is the depth term, which is T4. We only had 2 depths that we looked at. So we looked at a surface rupture and one at 5 kilometers. What we don't know is is it linear between 0 and 5 kilometers depth? Is it maybe parabolic? We don't know. And so for that, we looked at it and we said, we know that there's a reduction in the amplitude by 30%. What is it at 10 kilometers? I don't really know. We don't have the simulations in order to rationalize that. So for now, we've just said, okay, for a depth of about 5 kilometers, you can anticipate about a 30-degree reduction in your amplitude. T5, and let me go to the next slide. So what we were previously talking about is if your hanging wall is a plus 90, so if you're within this area here, you were going to use all those others. If you're off the sides, So if you're coming off in here, let's say that you're at a station here, you're not going to have the same amount of amplitude as if you're right over, this plus 90 degrees. And so we developed a taper so that if you're within Ry of L over 2, so you have your length divided by 2, Ry, just as a reminder, Ry comes from the middle of your fault, and it goes in this direction. This is positive Ry, and this is negative Ry. So if you're L over 2, if you're within this area, then your taper is basically equal to 1. As you come off the sides, you're going to reduce. So here, if you're in this area here, your taper is equal to 1, and then it falls gradually in a linear fashion until you get to this blue line or the pink line, and then once you get past these lines, it's equal to 0. So basically, it's just tapering it over the sides. So that's what that is for the side tapers. Okay, so we took a look at the surface ruptures. And then I just want to real quickly, I normally show at this point about 130 slides. I'm going to just condense it down now to about 4. We took a look at what is the difference whenever you apply that model onto the simulation results. So we're going to look at the residuals. So what is the blue line? Actually, what is the red dots minus the blue line? And so these are the residuals that you get in LN units. So 0 basically means that you're right on the model. And so as you can see, for each one, they're actually pretty close. We're mainly within about plus and minus 0.3 residual on either side, which is pretty good. Here's the magnitude 6 for dips 30 through 70. This is magnitude 6.5 for 30 through 70 also. We did have some problems here in the 30-degree dip, but we think that has something to do with the simulations and the velocity model that we were using. This is the magnitude 7, so we had several different lengths and widths that we were able to use. Once again, we're constraining pretty well within the plus and minus 0.3 area. This is the magnitude 7.5, and again, we're constraining the model pretty well based on the simulation results. For the buried ruptures, as I said before, really all we can do is apply about a 30% reduction in our model. So here we actually got a very good fit with about plus or minus 0.2, and then here about plus or minus 0.3. And with that, are there any questions?
Great. Thank you very much, Jennifer. I appreciate that. A couple of questions for Jennifer on the hanging wall one. Zifa.
I think you probably have done this. So have you tried to validate the simulation model with the actual observed ground motion? How is there systematic deviation? Thanks.
Yes, actually, some of the developers are going to show that. Whenever they ran this against the empirical data with their models, what they found is that over the hanging wall, it was able to match the data very well. But once you got off of the hanging wall and you started to move in greater distances away, the amplitude fell quite rapidly. So it fell more quickly than what the simulation data had. So a lot of the developers have used the same model over the hanging wall portion, the surface projection of the hanging wall, and then used their own tapers as you came off the sides.
So, Zifa, that's a good question also. In general, all these supporting research projects, they provide models or any other things. Then the developers that they rely almost heavily on empirical data, they take it, they examine it, and then they said, oh, this, as Jennifer said, it works in this range, but it doesn't work in the other range, and so on. So ultimate responsibility will be with the GMP developers because they check it against empirical data. Like nonlinear soul response is the same thing, hanging wall and other things. Any other question for, however, we needed that study because, as I mentioned, we don't have so many empirical data to show for different dip angle, for different magnitudes, and so on. So that gives us a clue. We put it into GMP, we run it against empirical data, then we decide. Yes?
Could you help me out with the geometry? Are we talking about a down dip rupture? And are we talking about the hanging wall? Are we talking about some sort of a waveguide effect up the dip of the fault plane? Or are we talking about right above the surface where the rupture occurred? Or is anything known about where the ground motion was actually generated?
The simulations were based on 30 different realizations, so different slips on the fault plane for each. For instance, for magnitude 7 at 30 degrees, they ran 30 different simulations, different slips in different places, so that I actually have some other models that show that you might have different higher amplitudes in different areas just depending on which model you used. And so we collated all of that into a median. So for each one of these, yes, there are 30 different realizations for each case. Does that answer your question?
The faults go down?
Yes.
Always?
Actually, it sometimes goes across, sometimes it goes slightly up, sometimes it starts in the middle and goes out in different directions. So there were very, very different, each one was different. So sometimes it went up and sometimes it went down.
Any other question? Last question? No? Thank you very much, Jennifer. I appreciate that.